Today's lesson is called Adding and Subtracting Radicals or Square Roots. So for the opening exercise, I'd like you to complete exercises A through D. The directions say for questions A through C, simplify each expression. And then in part D, it says explain how you simplified the expressions above. That's the only portion that you should be completing for the opening exercise. When you get to the word main idea, that's what we will be moving on together. So at this time, please pause the video, complete the opening exercise, and then resume the video to go over the answers. Okay, you had a chance to try the opening exercise, so let's go over the answers. For A through C, you're supposed to simplify the expression. So in letter A, you have 3x plus 5x. Those are considered like terms. They have the same variable of x. And technically, the exponents on x are 1s. So you're allowed to combine them by adding up the coefficients, just the numbers in front. So 3x plus 5x should be 8x. In part B, you have 8y squared minus 2y squared. So again, they are like terms. You can subtract the coefficients. 8 take away 2 is 6y squared. Notice that I'm keeping the variable and keeping the exponent the same. They are not getting touched. I'm just adding or subtracting the coefficients. And then in part C, I had some that were like terms and some that were not. 9r was kind of standing on its own. And you can see I coded 2t and negative 6t as like terms. So my overall answer would be 9r minus 4t. So explain how you simplified the expressions above. Hopefully you wrote something about combining like terms. You could have said add or subtract instead of combine. You could have described what like terms are, like same variable and exponent. And I would also like to say that you keep these. So we might want to put that underneath. We're not making y squared and y squared into y fourth. It stays y squared. So we'll move on together to the main idea. For the main idea, we can add and subtract radicals in a similar way to combining like terms. We can only add and subtract quantities with square roots that have the same index. So this is kind of your vocabulary from the prior lesson that we'll talk about. And it's similar in the fact that you're looking for like things. So underneath, we are now going to refer to this as like radicals. So again, you can only add and subtract quantities with square roots that have the same index and radicand, which is the number under the square root. And we're going to refer to these as like radicals moving forward. Okay, so very similar to like terms. You want like radicals. So in order to add or subtract radicals, you're going to follow the steps below. First, just like combining like terms, you're going to identify like radicals. You've got to find the things that are like so you know what you can combine and what you can't. Special note underneath, when the radicals in an addition or subtraction problem are different, you do have to check to see if they can be simplified before you decide if you can add them or not. So it may be the case that when the radicals are simplified, they will actually become like radicals, which means you will be able to add or subtract them. And then step 2, for the like radicals, you'll add or subtract the coefficients and keep the radical. Again, very similar to combining like terms. If I go back up and look, we found the like terms, x's and x's. We kept the x, we just added up the coefficients. In B, y squareds and y squares, we found the like terms. We did the operation on the coefficient. Same thing here. We're going to find the like radicals, do the operation on the coefficients. But remember, if they don't appear to be alike at first, we should simplify them like we learned in the last lesson to see if we can actually add or subtract them. So we're going to go through some examples together. In example 1, first thing we want to do is identify the like radicals. So do we have like radicals here? Square root of 11, square root of 11. These are like radicals. You can see that, like and like. So we are just going to take the coefficients, which means the 6, and add it to 9 to get 15. So the answer here is 15 square root of 11. Now, just like any answer, I should look to see at the end if I want to simplify it as well. Like if I was working with a fraction and I got the answer 6 over 3, I wouldn't leave that as my answer. I'd just make it 2. So I should still look and see, can this be simplified? It cannot. Square root of 11 is as simple as it's going to get. Okay, let's try number 2. So do we have like radicals? I see square root 3, I see square root 3. So once again, this is an example with like radicals. So the first thing I want to point out here is that square root of 3 looks like it's just square root of 3, when in actuality there is a coefficient out in front. It's a 1. So you might want to take time to rewrite this as 1 square root 3 minus 5 square root 3. Because then you'll see you're going to take the 1 and the negative 5 as your coefficients and combine them. So 1 take away 5 would be negative 4. So this is negative 4 square root 3. And again, looking to see if I can simplify, square root of 3 is as simple as it's going to get. So there's two examples right away of like radicals that are there, easy to find, either just add the coefficients or subtract the coefficients. Let's move on to example 3. Here, when I'm looking at the radicals, I see square root 12, square root 12, square root 12. So I once again have like radicals. So I can take all of those coefficients. I'm going to squeeze a 1 in there because that's really negative 1 square root 12. And we're going to add everything up. So I've got 4 take away 1, which is 3. And then add 6, which gives me 9 square root 12. But I'm going to stop. Square root 12, is that in its simplest form? Answer is no. So we're going to put a little star here, and this is the first example of one that's actually not simplified. Which means at the end of the problem, we need to simplify the radical like we learned in our prior lesson. So this is going to become 9. And now that we learned how to simplify radicals, I want to show you that you can just put the factor pair under one radical. If you want to continue to do the two different ones like we learned in the previous lesson, you can do that until you get more comfortable. Square root of 12. I want the largest factor that goes into 12 that's a perfect square. So the largest perfect square factor of 12 would be 4. What would I need to multiply 4 by to get 12? That would be 3. So then underneath, I'm going to have 9. Can I take the square root of 4? Is it a perfect square? Yes. So the square root of 4 is 2. That's going to come out. Can I take the square root of 3? Is that a perfect square? No. So it stays underneath. I leave it under there. And then 9 times 2 makes 18. So there's an example where everything was like radicals, but it had to be simplified at the very end. Now in number 4, it's a subtraction problem. Before subtracting, what do you notice? So take a look at that problem. What do we notice? Hopefully for the first time you see, we have unlike radicals. Okay, so right now it looks like I can't do anything with this. So if you remember, when I go up here, we got to look at this double star moment. It says when the radicals are different, we have to check to see if they can be simplified first, because they might end up becoming like radicals after we simplify. So we're going to go take a look and see if we can simplify. We can. We just did the square root of 12 above. So we know we can simplify that. So this is going to be 5 square root 3 minus, and you can put the 1 in there if you need to, but you don't have to have it. We're going to break 12 down into 4 times 3 like we did previously. So this is 5 square root 3 minus, we know we can take the square root of 4 to make it 2 and come out of the radical. 3 is not a perfect square, so it's going to stay underneath. And now you can see we have like radicals. So 5 take away 2 gives us 3. This is 3 square root 3. So let's move on to number 5. Number 5, it does not look like we have like radicals. So we're going to do what we did before. We're going to simplify. And let's actually go up here underneath here and write a little note that we had to simplify first in order to check that, because a very similar thing is going to happen in our next problem. Number 5, it looks like we don't have like terms, but we can actually simplify the square root of 80. So the largest perfect square factor of 80 is 16. So this is going to break down into 16 times. We'd have to multiply 16 by 5 in order to get 80. And then plus square root 5. So can I take the square root of 16? Yes, it's a perfect square. The perfect square root of the square root of 16 is 4. So that's going to come out. 5 is not a perfect square, so it stays underneath. That's going to get added to square root 5. So this is really 4 square root 5 plus, remember, 1 square root 5, which means the answer here is going to be 5 square root 5. So very similar to number 4 is it needed to be simplified first. All right, let's look at number 6. It does not look like we have like radicals, so we're going to simplify. This time, however, we have a nice simplification. 5 square root 7 stays 5 square root 7. And then minus square root of 49. 49 is actually a perfect square. So the square root of 49, 7. So we have unlike terms here. We have a number and then we have a radical. And those two things cannot be written together. And there's a special little note about how to write this. If you're not careful, it could look like the minus 7's underneath the radical. So rule of thumb, we're going to write the rational number first. Right, rational number first. So the way we really want to write this answer is negative 7 plus 5 square root 7. And that's definitely something we want to get used to because that will come up in future lessons. Now let's look at number 7. Before we add these, because I see it's an addition problem, what do you notice? Take a look at that. Hopefully you notice that there's actually a variable as part of the coefficient. So we're going to write there is a variable as part of the coefficient. So we just have to add like terms just like we always have when we have like things. So let me show you what I mean. Are the radicals alike? That's still step 1. I've got square root 7, square root 7. I have like radicals. So we said to take the coefficients, that would be this part and this part, and do the operation. So we're still going to do that. 3x and 2x makes 5x. So don't let a variable out front throw you off. As long as there are like radicals, you add the coefficients. If that means the coefficients have variables and you have to actually add like terms, that's okay. That x is not a multiplication symbol. That is x variable. Okay? And then our last one, number 8, is a subtraction problem. But before we subtract, what do you notice? I'm hoping that you see that we have different things on the outside of that radical. So it's not the same index. I have an index of 3, and then remember when you don't see one, it's actually an index of 2. So these are actually not like radicals. So not like radicals. So that means my answer is exactly what my problem was. Cube root of 14 minus 3 square root 14, and that just is my answer. There's nothing I can do with that. And that concludes our lesson on adding and subtracting radicals or square roots.